So look at the anatomy of the pillar drill. Now you've got really nice machines at CME. This is a entry level, very cheap pillar drill. It's single phase, it's not got an awful lot of power, it's not got an awful lot of flexibility. The anatomy however is exactly the same. So on the front here we've got different speed ranges, and these are controlled in this instance by moving the belt on these different pulleys. So you have to manually change the gear, as it were, by getting in there and changing the position of the belt, which makes it a little bit slow to use, a little bit clunky, not as nice as your machines, which have got little selector levers to actually control the speed of the shaft of the drill. On the front here we've got the actual speeds which are available. In fact there's two options, 50 and 60 Hertz, depending on where you are geographically in the world. Europe uses 50 Hertz as their supply frequency, so the speeds available on this particular machine range from 525 at the slowest through to 2660 at the fastest. There's not an awful lot of options in here. When you're assessing the speed to drill at, the first thing that you need to do is go to the chart on the wall in the machine shop and do the calculation based on the material and the size of the drill that you're doing. That will give you an RPM figure. Now if for example that RPM is 1100 RPM that you need to be drilling at, as you see on here, I don't really have that option. I could choose 916 or I could choose 1330. I can't choose the speed that the calculation tells me I need to be using. So it becomes a judgment call. You have to take a little bit of a shot in the dark. I would, generally speaking, start on the slightly slower speed. It's a little bit closer but not by much, 916 RPM. I would then try cutting. If it cuts nicely, if we get nice swarf coming out, your job is done. Happy days, move on. If it doesn't seem to be cutting particularly nicely, stop and change it up to the speed on the other side of the target that you're looking for. Although a lot smaller, this is exactly the same in terms of anatomy as the drills that you've got at CME. We have a set of handles at the side that we can use for raising and lowering the chuck. The chuck here is a keyed chuck. Most of the chucks that you'll come across on pillar drills will have keys in them. They come in all different shapes and sizes. Here's one from my lathe, and another one. This one is slightly different. It's a keyless chuck, but basically exactly the same thing. You have three jaws. The three jaws come down and grip onto the shank of the drill, enabling it to transmit the force from the motor. Be wary, all the keys are different sizes. As you can see from this one, that's far too big to fit in there. Make sure you find the correct size of chuck key, otherwise you're going to do damage to both the chuck key and the chuck itself. So the chuck is supported on this shaft here, which we call the quill, and that's the actual bit that can lower down whilst the drill is rotating and allow you to drill into a piece of material. We can, in this one, we can set up the depth stop at a particular point by putting the two bolts into position, so we could repeatedly drill to the same depth. And as you can see, it's spring loaded, so that the return, the upward movement, is controlled by a spring on the side here, rather than you having to physically lift the drill back up into place. Now this is a real small entry-level drill. These days you can pick one of these up for less than £100, which, considering what you get, is a really good bargain. It's massively limited, but if you're looking at setting up a little home workshop, this is probably one of the first proper machine tools that you will buy. At some point in the future I will upgrade, but for now this is working perfectly well and is doing everything that I need. One of these, as I say, the kind of price that we're getting for one of these, under £100, I could probably buy, I would say, about 30 of these for what one of the drills at CME costs to replace. So you can see the equipment that you have is really gold standard and very high quality. This drill suffers with the same problem as the drills that you have in the workshop. It's a minor problem, but it can be an irritation. It's something to bear in mind. The shaft which supports the head of the motor is a round shaft. Round shafts are easy to produce, they're cheap to produce, they're easy to get quite accurate, and they're fairly easy to clamp onto, which makes them very advantageous, and you'll find most of the pillar drills that you will buy will have a round shaft. It means that we've got almost infinite variability in the positions that I can put the table. It can swing through 360 degrees quite happily. I can move it right out the way and actually work directly on my bed. However, it has a significant problem. Quite often what you have to do, you'll start off with a small drill, and you might drill a pilot hole, come back up, and then you're going to need to put a bigger drill in. The bigger the diameter of a drill, the longer it gets. So as you can see, this one, which is over 25mm, about 28mm drill, is massively long and doesn't stand a chance of going in there. So once we've drilled our pilot hole, next thing we need to do is lower our bed down. The issue there comes with, because this is a round shaft, the moment we undo it to lower it down, it's able to move from side to side, and that critical alignment I had with the drill is gone. It's always worth planning, because you've got quite good length of travel on your quill, much longer than I've got. I would set it up so that when you're putting a centre drill in, make sure the centre drill will come down and make contact with the work when the drill is right down low. So I can now centre drill, it's not very straight, put that in. So I can now centre drill at full extension of the drill, so that when I come back up, I can then take the centre drill out and I can put my much longer drill in without having to move the bed. You will do it, it will happen a few times, and then you're going to have to rethink and work out how you can relocate on the original hole that you made with the centre drill. But nevertheless, it's something to bear in mind, because it's a significant problem with round shafts, but it's something you're going to have to get used to. Jacob's chuck. So we not only need a key, this one is usefully attached with some chain, because I tend to lose stuff. There's normally somewhere on the drill that will allow you to hang those in place so they don't go missing, but I guarantee when you need one it will have gone walkies. Let's look at mounting a drill in. First things first, just by hand we can open up the jaws of the chuck and then twist them so that they re-grab the drill and have it in position. And sometimes it's worth just spinning it by hand, make sure it looks roughly straight. That's obviously not tight enough, you can't tighten it enough by hand, we need to use the key. It's one of the quirks of the Jacob's chuck that it's got 3 holes in it, obviously for easy access, but we actually need to use each one of them. So although this is one solid piece and this lock ring is one solid piece, and you would think just by putting the key in and giving it a nice twist to tighten it would be sufficient, but because when we twist this it tends to just lift this over to the side a little bit and lock it in position, what we actually need to do is, once we've done one side, we rotate it round to the next hole, put the key back in again, and you'll get just a little bit more of a twist. Round again, last hole, back in, get just a little bit more of a twist without putting any more effort into it, because each time this is just knocked over just a little bit and it's bound up on the top here and grabbed, and so by moving it to another side it frees that up a little bit and allows you to just get a little bit more movement. That is now securely located in the chuck, ready for drilling operations. Before we even think about starting to drill, we need to consider work holding. So on a pillar drill there's probably going to be 2 options you're going to have. You're either going to have a machine clamp like we've got here, or you're going to use a vise. Start off with a machine clamp. So I've set this up holding this little bit of mild steel bar here. This is the standard kind of setup you'd expect from a machine clamp. Now you may have large triangular, look like flights of stairs which go under the back end here. I don't have any of those here, but you've got plenty of them over at CME, or you may find some of these clamps, which are actually apprentice made clamps, lurking around in the machine shop that you can also use. Notice the setup. There's a few key points that we've got here. First of all, the actual clamping bar. Now if we look with the spirit level, what we'll see, there's level, and the actual position, it's pointing slightly downhill towards the work. That's critically important. That's putting all of the load onto the workpiece. Not very much load is being transmitted to the back, it's all being transmitted to the front. That's key number one, and that's the most important setup that you can get. You can tolerate it being level. What you can't tolerate is for it to be pointing down towards the back of the clamp, because then all the load will be at the back of the clamp and it won't be doing anything effective in terms of holding the material. How these function is they generate significant amounts of friction between the workpiece and the actual bed of the machine, and that's the only thing that holds it in place. It's not physically held any other way, but with the friction generated between the two. So it's vitally important that we make sure the bed is clean before we clamp anything down to it, and make sure the work is clean before we clamp anything down to it. Make sure there are no burrs on any cut edges, because they will lift it up slightly and preventing that full contact, which will generate lots of friction. The clamping bolt itself, we need to locate that as near to the front as is possible. That's not always that practical, and you'll often find you end up having to have the bolt towards the back here. It's not ideal, and we always need to think in the back of our mind to keep this close to the work as is possible, but sometimes you just have to get it as close as you can and leave it at that. That's why having that slight downward angle will help increase the load to the front, even if this clamping bolt is at the back. And you'll either use the triangular block under here, or if you've got one, a bolt that you can use to apply extra load to the front that's holding the item in place. Second option with mounting is using a vise, as we've got here. Again, we're still relying on friction, so we have two bolts which are clamping the vise down to the table of the drill. That is generating the critical friction that we need between the two, which will stop it from moving about. In an ideal world, if I had a bigger table, I would have another bolt at the front here actually supporting this to increase the amount of friction right the way across the entire vise. Nevertheless, these are not stopping it from moving physically. These are just being stretched slightly by doing the nuts up, which is causing them to act like elastic bands and clamping this down hard against the bed. They're not physically stopping its movement. In fact, if we took carefully one of these out, we might see that the bolt itself is not touching any part of the vise or the gap in the bed. Only the head is making contact. So friction is critical, and again, make sure that the bottom of your vise is spotlessly clean, and make sure your table is spotlessly clean before you make any clamping operations. For holding the actual work, we've got a couple of options. We can use this notch that we've got actually machined in the top lip of the vise here, and if we've got something nice and square, we can use that to help locate it. And as we do the vise up, the square side of the material that we've got here will locate and keep the unit square, and this will hold it in place. This prevents there being any chance of the material slipping down and going down into the open throat of the vise as we apply pressure from drilling to the top. So this is ideally suited for nice square pieces to get them spot on. But even with something like that, it's worth applying a level just to make sure that the item is perfectly true before you start machining it. This material is a little bit different. It's subtle, but there's a radius on the outside edge here. Now if I try and load that in and use that very same slot, we can put it in at an obvious angle, and because of that radius, it still clamps up, it still holds, but it's no longer true, it's not reliable. So you wouldn't be able to use that kind of little slot on the top of your vise in that kind of situation. And here the simplest thing, if it's not precision, now if it's precision you need to get a set of parallels that you can lay in the bottom of the vise here and use them to hold it up. If we're just doing a little bit of drilling, sheet metal, bench fitting, etc., and it's not within thousandths of a millimetre accuracy, we can just apply a piece of square wood that we've maybe cut up on the bandsaw. And what that will do is twofold. It gives us something that we can push down against, and if we've cut it nice and accurately, that will ensure that our item is nice and square to the bed of the table. And secondly, it does that same thing as that little notch does. It will prevent the material from sliding down in the vice jaws as we apply a load with a drill. It's critically important to make sure that the piece of wood we've produced is narrow enough so that it sits between the gap in the vice jaws. Otherwise the vice will clamp on the wood and won't really grip the material that we're trying to drill, although it may feel like it has. Either of those two options are ideal. What we don't expect to see is anything being held by the hand. The chances of a drill snagging on a piece of material as you burst through the outside of the material is very high, and when that happens you've basically created a miniature helicopter with sharp bits of metal spinning around at high speeds. To never ever have anything held in your hand when you're drilling it. Always find some method of holding it firmly so that the vice and the pillar drill itself are doing the work for you. Right, so we're set to drill. Piece of mild steel in the vice. Got it mounted on our piece of wood, which is quite snug in there. I've blued it, I've deburred it after cutting it, and I've scribed a couple of lines so we've got a point at which to place our centre punch mark. The centre punch mark I've made large enough so that the tip of our drill, our centre drill, will locate in there nicely. Obviously here I've removed all the guards. You'll need to have gone through all your standard safety checks to make sure the machine is safe to operate and that the e-stop works and that the guarding works. So once we're set up, I'm just going to turn the drill on. Then I can bring the drill slowly down. It's much easier to see if we've got our centre correct with the drill spinning because the point doesn't move. And yes, that's located in there nicely. Once I've done that, I can just start drilling with the centre drill. Now I'm not going to go any deeper than that. I don't really need to. I'm only doing a little 6.8mm drill in here as a demonstration. If you go right the way down to the angled portion of the centre drill, as your drill comes in it's going to be very noisy, it's going to cut unpleasantly, and there is a risk, as you can see here, that you could actually make your centre drilled hole larger than the hole you want to produce. So I've got enough there to make sure that this will follow the path nice and accurately, but it will still cut nicely. So I loaded in the 6.8mm drill. I've recentered it because I had to drop the bed down, and now we're going to actually drill the hole that we want to be the finished size. So now initially I'm going to do this wrong. I'm not going to apply enough force to the handle. That's a little bit out. Sometimes you can just tap the bed across just with a right hammer blow just to get it to locate a little bit better. So the drill's cutting, but what's coming off is really filings, tiny little bits of razor sharp swarf. It's done very little, and you can actually hear there's a little bit of chatter forming on there. So what that drill is doing is that drill is rubbing. That's not the correct way to drill. I'm not applying anywhere near enough load to the drill to get it to cut effectively. What I want to see is long twists of material coming out that is taking heat away from the metal I'm cutting and from the drill itself. These little bits are not coming out sufficiently fast enough to take the heat generated by the friction as this rubs on the metal. So the tip of the drill will get hot, which means the metallurgy will change. The temper that we carefully manufactured into it will be lost. It will become soft and start to distort, or it may even become hard, and start to become brittle and will break on the edges, depending on how hot we get it. Let's try and drill it a little more correctly. So it went quiet once it went through the centre drill hole, and now the whole body of the drill is engaged in the work and it stops making those annoying chattering noises. Now if you see what's coming up, and I'll show you some when we go through, we've got little dense spirals of metal coming out, quite thick. I'm going down a little bit, waiting for them to become about 10 millimeters long, and then I'm just backing off with the drill. So you're going down in a sort of pecking motion. So that prevents those spirals from becoming so long that they're whipping around the machine and could cause you a risk. So we just peck our way through, looking for that nice clean swarf coming out, and you can hear the machine is loading up a little bit. In fact, on this little drill you can even see it moving ever so slightly. Now I'm nearly through, so I'm just going to ease up a little bit on the pressure. And that's just the sound of it breaking through, nice and gently on the last bit, and we're through. And we can tell we're through in this instance because a little bit of sawdust has actually come up through the flutes of the drill. If we look at some of the swarf that's been generated now, see we've got these nice spirals. These are sharp, these will cut you, but they're thick enough to have some degree of rigidity, almost a bit springy. And what that will do, that will come off carrying all the heat that we've generated in the drilling process and throwing it away. That's exactly what we need to see, and you can control that by how much pressure you apply to the handle. So the key to this is watching the swarf as it comes out of your drilled hole, and that will give you an indication of exactly how much pressure you're applying and whether you need to push a little bit harder. If obviously you see the drill slowing down or coming to a stop, you're probably pushing too hard, but you're going to have to really hang off of that handle to get it to do that. But you should certainly feel it in your arms. It should feel like you're having a little bit of a tug of war with the pillar drill as you force the drill down through the material.